So today, we're going to be working on linear algebra, and we're really going to be working on, section 1.4, 1.5, and 1.6 stuff here. And, but if you look at, hopefully you've come over here and looked at your assignments, all right? You should have already gotten the book and gotten the access code and all these things, because I'm already setting stuff up for you guys. I've got a homework number 2 coming soon. I didn't mean to, okay, but it's there. I haven't put the dates on it and stuff like that yet, but it's there. But right now you should be working on homework number 1. This is your online homework number 1. The other thing is you've got your traditional homework number 1, and this is, I've kind of got some templates here set up for you guys and stuff like that. So this is the one you should be working on right now. Let's take a look at it real quick, okay? All right, probably easier for me just to download this thing here, put it this way. So if you look at this guy, look at the kind of questions that we're getting and stuff like that. So read the directions. This thing I've got is going to be due on September the 6th, if I remember correctly, that I put on this thing. All right, look at the questions. All I ask for is whether these questions are going to, these systems of equations are going to be consistent unique, consistent infinite, or inconsistent. So you didn't actually have to solve this thing, but you had to do your kind of matrix reduced echelon form to a point where you can go, clearly this is going to have, pivots here, and I'm pretty much going to get a unique answer or infinite number of answers. Or look at that, 0 equals a number, that's going to be inconsistent type thing here. Okay, over here, your job is to actually use these matrices and think of them as augmented matrices, so they're system of equations. I put this weird letter H or K in there, and H and K in this thing, and you're supposed to tell me the value of H and K that would actually make this a consistent system. Please tell me about consistency. You were consistent. There's 2 kinds of consistent. Consistent unique means you get exactly one answer, or consistent infinite. That means it's still going to have answers, but it's going to be an infinite number of those type of answers. I don't want inconsistent. Does that make sense? Inconsistent is zeros augmented with a number that's not 0. So you've got to tell me the values of H and K to make this matrix, which represents a augmented matrix to a system of equations, making the answers consistent. All right, so this one, I wanted you to take this guy and find the reduced echelon form. Show me your work. It's not just about, I got a calculator to do the problem. I want to show me the work to actually get this reduced echelon form. There's 6A and 6B there. This right here, we're doing vectors, and so I want you to take these 2 vectors, I want you to add them, take 2 times the first one plus minus 3 times the second one, a negative u vector, and what is the v minus u vector going to look like? Here I got A1, A2, A3, and B, so here's a system of vectors here, and I want you to determine whether this vector B is in the span of these vectors, okay? I'll talk about that in a second here. All right, so, and here I want to determine whether these 4 vectors right here actually span all of R4. What is R4? R4 is the 4-dimension thing, in terms of vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 0, 0, 0, 0, 0, 1, okay? The 4 vectors on this thing, and the only way it's going to be able to span that is each one of these vectors, when you do kind of a reduced echelon form, you should get a pivot for each one of them. A pivot is telling you this is an important vector as part of the solution. So if you get 4 pivots, then it's going to span R4. If you only get 3 pivots, it spans, well, don't worry, we'll get these terminology later, a subspace of R4, so forth and so on. Compute the following matrix products. I want you to multiply this matrix times this vector, if you will. Vector is a matrix. And then I got you some questions about the size of matrix and augmented, whether you get unique systems and stuff like that. So all in all, I got 16 questions on this thing, but it is due when? Next Tuesday. So we've already covered this stuff. I just kind of want you guys to see that it's due next Tuesday. Yes?
Just for clarification, did you want us to print this out right on that sheet?
Yeah.
And upload it, or can we?
No, don't upload it. Bring it in class.
Bring it to class?
Yeah, we want to take it up. See Jacob over here? He's my grader.
Okay.
He's my new grad student.
On that sheet, we can like rework on a separate piece of paper?
can if you want to attach it to it, just be organized. Remember, the man over here is grading it, make it easy for him. Okay, so make it organized, stuff like that, don't write sideways and stuff like that on it, make it organized. All right, but I did, again, want to talk about that aspect of it. It's due, and there's something else due. What else is due? Wait a minute, what else is due? Back to the, because if you've got one, I always put this stuff in pairs here. You've got your, quote, online homework type thing here. There it is right there, homework number 1. That is also due on the 6th as well. And there are 30 questions. Some of them are real easy. Some of them are a little more challenging, but not overly challenging and stuff like that. And as you're also getting used to the computer system on entering answers and stuff like that on this thing, okay? So, but this, both of them are due, but this is the one you're going to turn in class. Yeah. No, it is not. This is that access code through the Pearson product. I thought about using WebWork, but if you've ever done matrices on WebWork, not that great. So I decided to go with the actual product from the company and stuff like that on this one. All right, so let's come back over here now, and let me get my screen up here. So here it is. And let's pick up where we left off last time, which is kind of like a homework problem. Here's one right here. It says this: let vector A1 be the 1, -2, 3 vector. Let vector A2 be the 5, -13, -3 vector. And let B vector be the vector -3, 8, 1. Okay? The question, and again we talked about this last time because this is big terminology here, is vector B in the span of A1, A2? The answer at the end of the day is yes or no, but you got to show me why. Okay? Now, here's the big deal on this one. Why? What's the big deal? To be in the span. What does it mean for a vector to be in the span? All right, terminology. For a vector to be in the span of a set of vectors, the vector must be a linear combination of those set of vectors. So B has to be a linear combination of the two vectors A1 and A2. In other words, to be a linear combination, there exists a C1 and a C2, and these are constants, also known as scalars, getting used to the terminology, such that C1 times vector A1 plus C2 times vector A2 will be equal to that B vector. That's what it means to be a linear combination of these two vectors. Does that make sense? Now, watch where I go with this. This means that C1 times the A1 vector there. A1 vector is 1, -2, 3, plus C2 times the A2 vector, 5, -13, -3, has to be equal to the B vector, which is the -3, 8, 1. There's got to exist. So in other words, I got to be able to solve for the C1 and C2. Okay? Now, shortcut, long cut method here. I'm going to go it the long way, but then you're going to see the shortcut very quickly. If you go back and look at this, you can rewrite this as an equation. C1 times 1 plus 5C2, first component plus first component's got to be equal to the first component, -3. -2C1 plus, or minus, plus negative or minus 13C2 has got to be equal to 8. And your third equation is going to be 3C1 minus 3C2 has got to be equal to 1. Does that make sense? You see how I went from vectors to back to equations. And that's what we're going to do a lot in this first chapter and show you the relationship between vectors, equations, and matrices. We'll get into the big matrices things here in a second. So, now, if I gave you this equation, instead of being at C1, C2, and whatever, maybe I could make it X1 and X2, it's the same thing. How would you solve this guy? What would you do? Augmented matrix. And if I wrote this as an augmented matrix, what would it look like? Well, the coefficients of the C1 is 1, negative 2, 3, 1, negative 2, 3. The coefficients of, we call it the coefficient matrix, 5, negative 13, negative 3. And it's equal to, so it's augmented with the B vector, which is negative 3, 8, 1. Does that make sense? Now, did I really need to write this? No, you can go right from the column vectors to the actual augmented matrix. Save yourself that much more time. Yes? Double check my numbers here. Yes, it is. Very much. I look down and look back up again. Catch me on that. I'm discussing this, not paying attention to numbers. I'm going to pay attention to numbers in about 10 seconds from now. So, my point is, did you see how I went from here to here is what I'm after. Now, how would you solve this thing? Solve for the C1, C2. This is where we do that reduced row echelon form stuff. I was nice enough to give you a pivot right from the get-go, right? So I double check. It's 1, negative 2, 3. It is 5, negative 13, negative 3, and negative 3, 8, 1. So now I've got him right. So I'm going to take this guy here, and I'm going to sweep down and kill these guys off. So sweeping down, I'm going to do negative, so positive 2 times row 1, add it to row 2, replace row 2, and I'm going to do negative 3 times row 1, add it to row 3, and replace row 3 with it. This leaves me with 1, 5, augmented with negative 3. Let's see here. Negative 2 times 1 is, positive 2 times 1 is, positive 2 plus negative 2 is 0. That's kind of the point. 2 times 5 is 10, and 10 plus negative 13 is negative 3. 2 times negative 3 is negative 6. Negative 6 plus 8 is 2. Double check my arithmetic on this. Okay. Now I'm going to swing down, kill off this 3. Negative 3 times 1 is negative 3 plus 3 is 0. Negative 3 times 5 is negative 15. Negative 15 plus negative 3 is a negative 18. Negative 3 times negative 3 is a positive 9 plus 1 is a 10. Agreed? Now, what's my next move? What would you do? And I'm going to make it the next pivot point. And so, because I could multiply by a negative a third if I want me to, but eventually I'm going to make him a pivot point if I need to. You know, I like pivot points being 1. But because this number is a negative 18, I don't think I'm going to make him a pivot 1 yet. He's still a pivot, but I won't make him that pivot 1 yet, because I would do this. I would multiply negative 6 times row 2, add it to row 3, and replace row 3. And if I did that, I would get 1, 5, negative 3, 0, negative 3, 2, and here we go. 0 times negative 6 is 0 plus 0 is still 0. Negative 6 times negative 3 is 18. 18 plus negative 18 is 0. Negative 6 times 2 is negative 12. Plus 10 is negative 2. Agreed? Now, I can make this guy a pivot and sweep up. Then I can make this guy a pivot and sweep up. Do I need to do that? Remember what the question is. This, we're trying to solve for C1 and C2. At the end of the day, to find the span, we need to solve for C1 and C2. And when I see something like this on an augmented matrix where my coefficients are 0, augmented with a number that's not 0, that right there tells me, what is it? Inconsistent. What does that mean? Now let's go back and answer the question. Is the vector B in the span of vector A1 and A2? No. Means no. B is not in the span, means element not. Okay, not in the span of vector A1 and vector A2. Does that make sense? If you could solve for C1 and C2, and there's two ways to solve it. I could have gotten a unique answer, maybe, or I could have gotten an infinite number of solutions. Either one of those, then vector B would have been in the span. But that right there says there is no C1 and C2 that I can solve for constants, so that the vector B is not in the span. Does that make sense? All right. And you see how this kind of connects to all that matrices and systems of equations stuff that we were dealing with. All right? So now, let's take a look at section 1.4. And here we go. Some little discussion with you guys here. All right, this is what we call matrix equations. So matrices are these rows and column block things that we've been playing with. And we got a whole concept of how to manipulate these guys, because matrices kind of act like numbers. So this is why this class, the Math 2164, is the prerequisite for something called modern algebra, because these rows and column block of numbers represent a style of numbers that you can manipulate. In modern algebra, we do a lot of math proofs. So abstract algebra, we do a lot of math proofs, but sometimes we need a good counterexample. Matrices are a great way to come up with a counterexample that you think things work, but not always. Okay? So, why this is a prerequisite class for higher level classes. So, matrix equation. Here's the matrix equation. A times x equals b. Now, A is the matrix. X is a vector called the variable vector, x. And b is what it's equal to, typically the constants on the other side. You look at that as a vector. So, matrix A times vector x. Matrix A, you're going to look at it like we did that last example. You'll notice that my vectors showed up in the columns of the matrix. So these are column vectors. A1 vector, A2 vector, dot, 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 AN vector. These are the columns. And this matrix here is going to be M by N. Rows by columns. You're going to have M rows of these guys, numbers, and N columns. There's N column vectors here. Okay? And then we're going to multiply it times the variable vector. What's my variables? My favorite guys. X1, X2, X3, dot, 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 down to Xn. Xn, because the number of rows by columns, this vector has to have the same number of rows as the actual matrix had columns. These n's have to actually match up. But this is going to be a vector. So a vector is kind of like a matrix, except it's by one. So this is by one. So this is my variable matrix, a vector, if you will. And then when you multiply, it's very simple. You multiply A1 times X1, you get that guy, plus, then you do plus the next term, A2 times X2, plus A3 times X3, plus A4 times, dot, dot, plus AN times XN. And you get this system. And this thing is going to end up being, this is M by N, and this thing is N by 1. The N's match up and cancel, so your resultant matrix is going to be an M by 1. So the sizes of these matrices are incredibly important, because they have to match up to be able to multiply. If they don't match up, you can't multiply. Okay? Yeah.
What does that say below the AN? Is that like N plus 1 or
N by 1. That right there? N times, N by. So you're talking about the dimension of these things. So I've got a question for you. All right, hold on. We go back to this problem over here that we just did. What size matrix is this thing right here? 3 by 3. 3 rows, 3 columns. Rows by columns. Let's see here. What size matrix is that? No, not 2 by. No, what is it? Rows by columns. 3 rows, 2 columns. Does that make sense? Rows by columns. And that's where the generic M by N comes from. This one is N rows, 1 column, N by 1. Okay? So, matrix A is M by N. That's the size of it. Rows by columns. And the AIs are actually the column vectors of A. X is a vector, which is kind of like a matrix, but it's by 1. N by 1. So you know, A is M by N. Vector X is N by 1. So when you multiply, when you do AX, you get B. And B, the N's match up and cancel. So the dimension is going to be M by 1 for the actual B vector. This is how you put these guys together. And here's the deal. AX equals B has the same solution set as the augmented matrix. If I was going to solve this guy, I put these A1, A2 vectors in there and augment it with the B vector, what it's equal to, and then your goal here is to solve. Solve for X1, X2, X3, dot, 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 all the way up to Xn. So there's still that same connection of solving AX equals B. You augment A with B, and you row reduce it, and then you can go back and solve for x. So note, ax equals b has a solution. You can solve. There's x1, x2, they exist. There may be a unique solution. There may be an infinite number of solutions, but if it has a solution, if and only if that vector b that it's equal to is in the span of the column vectors. So you see how we're kind of tied this into the last section, that the column vectors of the matrix, vector b is in the, quote, span, as a linear combination of the column vectors of A. So, big theorem down here. The theorem says this. All right, and in mathematics, you're going to get used to this when I get you guys into higher and higher level maths. The following are equivalent. It's a classic theorem that means the following, you get one, you get them all. So if you get just one of these little statements, all the other ones are going to apply. But we're math people. Math people can do things very well. They're very analytical, they're very smart, they can do lots of wonderful things, but one of the things they can't do, two things they can't do is read and write. Because we're math people, we don't like to read and we don't like to write. So we abbreviate everything in math. When you guys get into upper level classes, you watch the professor, he'll abbreviate everything on the board. That's what we do. Question? All right, but I'm after this one right here. All right, so theorem. It says for the following are equivalent. And get used to this. TFAE. You know what TFAE stands for? The following are equivalent. It's classic math professor stuff here. All right, here we go. For all vector b in the dimension Rm. What does this Rm mean? That means that this is a vector that is m by 1. It is a vector in R, which means all the entries came from real numbers. And that means that's the m, but since it's a vector, we don't put the by 1 in there. We just put the Rm. This is a m by 1 vector. Ax equals b has a solution. So if you have a solution for this equation here, then the other ones are equivalent. For all vectors b and Rm, b is going to be in the span of these column vectors of A. So if b is in the span of the column vectors, the equation Ax equals b has a solution. If one happens, the other happens. If this one happens, the other one happens. The span of A1 through AN will be equal to that whole dimension of Rm where b came from. And here's the other big deal. If you look at it from take my matrix and do that old reduced row echelon form stuff here, here's the deal. Matrix A has a pivot in every row when A is put into reduced row echelon form or reduced row echelon form. When you look at those, every row, you're going to get a pivot in every one of the rows. Okay? That's another indicator that you'll be able to solve this thing. It may be infinite or unique, but you're going to be able to get a solution on these things. The following are equivalent. You get one of them. All the rest of them will hold for free. So, let's do a problem. You guys don't learn anything until I actually do math out here on you guys. So let me pull this up, and let me put this underneath it. All right. The existence of a solution. Now, this one's going to be kind of strange, so here we go here. I'm giving you a matrix A. What size is matrix A? 3 rows, 3 columns, 3 by 3. The matrix A is 1, 3, 0, -2, 1, -2, -3, 5, -4. Traditionally, when you read a matrix, you read it down the rows. Vector B is going to be the famous arbitrary B1, B2, B3. These are going to be your constants here. The question is this. When does the equation AX equals B have a solution set X? When can you actually solve for an X1, an X2, an X3? When are you going to get a solution set on this guy? That's the big question here. All right. So, if I was going to do this, so let me go back and write this right here. I'm going to slide it up for you guys so you guys can see this. Put it over here. All right. I want a nice clean sheet of paper on this thing because it's going to take me about one sheet of paper to use. If I talk about AX equals B, You told me a few seconds ago, what is the best way to actually, when you're going to solve, what is it going to look like? You use an augmented matrix, right? What would the augmented matrix be? It would be coefficients of the coefficient matrix, matrix A, which is 1, 3, 0, negative 2, 1, negative 2, negative 3, 5, negative 4. But what are you going to augment it with? What do we augment it with? Not x. X is what you want to solve for. You augment it with what it's equal to, which is the b. But I gave you guys something weird here. I didn't give you numbers this time. I gave you letters. B1, B2, and B3. Okay? And we want to solve for this elusive x1, x2, x3 on this thing, if we can. So, again, remember what the question is. When does this ax equals b have a solution? Is there a certain kind of condition that's going to make this guy have a solution? All right? So now that we've taken the matrix A, which I gave you the numbers on that, augmented with the arbitrary B, so we want to kind of get a feel for what B is going to look like. All right, so here we go. How would you solve this thing? We're going to solve for x1, x2, x3, which is your variable matrix, in terms of B1, B2, and B3. That's basically my goal here. How would you solve this thing? What would you do? Again, I was nice to you guys. Notice I put in first row, first column position. What did I give you? A pivot. I would sweep down and kill off the guys below it. I'm going for my reduced echelon form. But watch what I do here. So in the first move, I'm going to take 2 times row 1, add it to row 2. I'm going to replace row 2. In the next one, I'm going to add 3 times row 1, add it to row 3, replace row 3. That would leave row 1 the same. 1, 3, 0, augmented with B. 1. What is 2 times 1 plus negative 2? 0. It's kind of the whole point here. What is 2 times 3, which is 6 plus 1 is 7. What is 2 times 0? 0 plus negative 2 is negative 2. What is 2 times B1 plus B2? That is actually 2 times B1 plus B2. You have to keep up with the moves over here. So for you computer science guys in here, think about what's being stored in the B1, B2, B3 column as I'm going through my reduced echelon form. Now, I'm going to sweep down. 3 times 1 is 3 plus negative 3 is 0. 3 times 3 is 9 plus 5. 9 plus 5 is what? 14. 3 times 0 is 0 plus negative 4 is negative 4. 3 times B1 plus B3 is 3 times B1 plus B3. So far, so good? What's your next move? Well, I can make this a pivot, but to make him a true pivot, make him a 1, I would have to divide by. Okay, I can do it, but maybe not. What's my real goal? To take the pivot and to sweep down. So this is your next pivot position, but you want to sweep down. And the next, the element below that is a 14, right? He's nice. What do I need to multiply by 7 to get 14? 2. And because they're the same sign, I'm going to do negative 2 times row 2. Negative 2 times that 7. That makes it a negative 14. So I can add it to row 3, that 14, and replace row 3 with that. So this is going to give me the matrix 1, 3, 0, augmented with B1. The next equation is 0, 7, negative 2, augmented with 2B1 plus B2. And now here we go. Negative 2 times 0 is 0 plus 0 is 0. Negative 2 times 7 is negative 14 plus 14 is 0. Negative 2 times negative 2 is 4 plus negative 4 is 0. Now watch this one. It's negative 2 times 2B1 plus B2 added to 3B1 plus B3. And I wrote it that way than the way I was going to write it because I didn't want to mess you guys up and show you exactly what I did. I'm actually, row reduction here. Yes, ma'am? Plus, no, that's a 3 right there, because we multiply 3 up here. 3 times 1 is 3 plus -3, that's what made the 0 down here. So this is a 3b1 plus a b3. Does that make sense? Yeah. All right, what do you need to multiply by 7 to kill off F14? -2. If you want equal but opposite. Does that make sense so far? Now, I'm going to clean this guy up. So what exactly is this? I can distribute. This is -4b1 minus 2b2 plus 3b1 plus b3. Let's clean them up some more, combine my terms. What is -4b1 plus 3b1? -b1 minus 2b2 plus b3, right? That right there is what he is. And notice who he's attached to. A row of zeros. So, if, by big IF, there exists the solution, x1, x2, x3, then what condition do we have? Then the condition, this -b1 minus 2b2 plus b3 has to be equal to what? If it's going to have a solution. 0. Why? Because if this guy is not 0, how does 0x1 plus 0x2 plus 0x3 equal number that's not 0? It can't. It's inconsistent. So the only way you can get consistent is your matrix, augmented matrix, must have a row of zeros. So if you've got zeros as the coefficient, the term on the right has to be a 0. Does that make sense? Okay? So, to describe the solution for this problem right here, could you please tell me some type of relation? Well, you can sit there and solve for B1 if you want to, move that to the other side, or you can say B1, it has to be equal to -2b2 plus b3, right? I solved for the pivot, if you will, on the B1 there. And so here is, you could have also solved for B2 or B3, but there is the relation right here. This is the condition that you have to have, the relationship between B1 and B2 and B3. Remember, we're trying to solve for this where AX was equal to B, and remember your B vector was very arbitrary. It was B1, B2, B3. The only vector that's going to be able to work here is you can put in anything you want to for B2 and B3, but B1 is going to have to be -B2 plus B3. That has to be the B1 position to actually have a solution to this matrix equation. Does that make sense? The condition on this guy. So, looking at matrix equations and how they fit together is this. I want you to compute AX. So, this is again another general form here. All right. And there's 2 ways we want to look at this stuff. So, all right. Gave yourself a matrix here. A, I gave you another 3 by 3. Why do we, honestly, I could do 9 by 9 or 45 by 45, but you kind of miss the point after a while if you got to write that many terms. So we do a lot of 3 by 3 on occasion, 4 by something or others, or sometimes 2 by something or others, but rarely ever a 1 by anything. So we kind of want something nice, big enough to get the pattern, but small enough that we don't hurt ourselves. So here's an example of matrix A. Let's compute AX. So I got here, A is 1, -2, 4, 3, -1, 4, -2, 7, -5. That's matrix A, 3 by 3. The vector X is my standard. Since this is 3 by 3, this is going to be a 3 by 1, X1, X2, X3. Classic column vector. What is A times X? The way you can look at this, if you multiply A, matrix A, times vector X, This is 3 by 3, this is 3 by 1, so it matches up, so you can multiply this. 3 by 3, and this rows by columns. This one is rows, which is 3 by 1. The only way you can multiply these properly is the number of columns on the first matrix has to be equal to the number of rows on the second matrix. They line up, match up, and cancel, and you're left with a 3 by 1. So the way you can multiply these guys out is look at it as this. AX is equal to, you take column vectors. 1, 3, negative 2 times x1 times the first guy. The second column vector, negative 2, negative 1, 7 times x2. The third column vector, 4, 4, negative 5 times x3. You can look at this, so your matrix is very big into these, putting the vectors in columns. So matrix A, which you take your columns and multiply by the entries in the vector that you're multiplying by. In this case, x1, x2, x3, the x matrix. Okay? And then, if you look at this, if you just multiply 1, 3, negative 2 by x1, you get x1, 3, x1, and negative 2, x1. You multiply x2 by negative 2, 1, negative 1, 7, you get negative 2, x2, negative 1, x2, 7, x2. And 4, 4, negative 5 times x3 is 4x3, 4x3, negative 5x3. And then you add components, and you end up getting the equational thing. x1 minus 2x2 plus 4x3, 3x1 minus x2 plus 4x3, minus x2 plus 7x, minus 2x1 plus 7x2 minus 5x3. That represents multiplying these two guys together. And you get that equational look to it. The other way, which is kind of the way you want to really look at this stuff, is matrix multiplication. Rows by columns. Again, this was matrix A, 1, negative 2, 4, 3, negative 1, 4, 2, negative 2, 7, negative 5. This was matrix X, vector X, x1, x2, x3. And how do you multiply? Row by column. First row, first column becomes first row, first column position. Row by column. 1, and you got them line up. 1 times x1 plus negative 2 times x2 plus 4 times x3. Row by row times column, and then you add them up. x1 minus 2x2 plus 4x3. Second row, second row column. Second row times that guy will give you the second row on your matrix here. 3 times x1 minus 1 times x2 plus 4 times x3. Third row, first column, negative 2 times x1 plus 7 times x2 minus 5 times x3. And notice we end up getting the exact same answer. There's only one way. There's more than one way to look at how you get these forms, but there's only really one form. Row by column and putting it how do you do matrix multiplication. So, with that being said, matrix multiplication is what we want to be looking at. So, I have some examples for you guys. Let's just do some matrix multiplication. Now, I know what your calculator can do for you, and I don't care. I want to see it worked out. I want to see how you actually do this stuff, not how a computer would do it. So, this first one, start out small. I got a matrix 1, 1, 2, negative 1 times a vector 2, negative 5. What size is this matrix? 2 by 2. What size is this vector? Rows by columns, 2 by 1. So your resultant, when you're done, is going to be the number of columns on the first and number of rows on the second should match up and cancel, and the resultant is going to be a 2 by 1. Let's see what we get. Rows by columns. I'm going to write it out only this time because this is my small case. This will be 1 times 2, 1 times 2 plus 1 times negative 5. 1 times negative 5. First row, first column, first row, first column position. Second row, first column. It's going to be a 2 times 2 plus negative 1 times negative 5. Now, put it together and let's see what you get. What's 2 times 1? That's 2. 1 times negative 5 is negative 5. 2 plus negative 5 is what? Negative 3. 2 times 2 is 4. Negative 1 times 5 is negative 5. Negative 5 plus 4 is negative 1. And you get a vector That is 2 by 1. And the resultant is -3. Oh, double check me on this one. Is that -1? Nope, I lost my sign there. -1 times -5. My fault there, lost my sign. What's -1 times -5? 5 plus 4 is easily fixed. There, watch the careless errors on the sign. 9. I'm writing it so small sometimes I don't see the numbers. Hint, hint, hint for you guys. Write bigger so you can actually see the signs. Because you lose a sign, bridge doesn't make it outside the river, people die. Your fault. Be careful. Watch the careless errors. What about this guy? What size matrix is this guy? 3 by 3. What size vector is this one? Look at it again. How many rows? 3 by 1. Okay? This is 3 by 3. This is 3 by 1. The 3's match up. So now my solution is going to be a 3 by 1. I got to line up and cancel. So here we go. Row times column and add them up. Now I'm going to do part of this in my head, so follow along. 1 times 1, what's that? 1. Plus 0 times 5, 0. Plus 6 times 0. Row by column, row, column. This is how you multiply matrices. First component, second component, third component, and then you add them up. We'll go back and add it up in a second. Second row, first column. 2 times 1, 2. Plus 4 times 5, 20. Plus -1 times 0 is 0. Third row, first column. 0 times 1 is 0, plus 1 times 5 is 5, plus 5 times 0 is 0. What do I get for my resultant? 1 plus 0 plus 0 is 1. 2 plus 20 plus 0 is 22. 0 plus 5 plus 0 is 5. I get the vector 1, 22, 5. And notice it is 3 by 1. 3 rows, 1 column. Does that make sense? Let's expand this. We don't have to have that n by 1 looking vector. We can actually have, a matrix times a matrix. So, what size is this first matrix? Very good. It is 2 by 3. Rows by columns. 2 rows, 3 columns. What size matrix is this guy? 3 rows, 2 columns. 3 by 2. What would my resultant matrix be when I'm done? See, the 3's end up matching and canceling, so you're left with a 2 by 2 matrix when we're done. Does that make sense? Row by column. First row, always start at the top row. First row, first column on your second matrix. What is 4 times 2? 8. What's 0 times -1? 0. What's 1 times 3? 3. And that'll be the first row, first column position. I'll get that number in just a second. Row by column. 4 times 2 plus 0 times -1, 0 plus 1 times 2. 1 times 2. That would be a 2. Thank you. All right? Now, first row, second column. First row, second column position. First row, 4 times 0 is 0. 0 times 5 is 0 plus 0. And 1 times 3 is 3. First row, second column position. First row, second column position. That lines up. Second row, first column position. -1 times 2 is -2. 7 times -1 is -7. 3 times 2 is 6, plus 6. First row, second column position. And then last, second row, second column. Second row, second column position. -1 times 0 is 0. 7 times 5 is 35, plus 35. And 3 times 3 is plus 9. So what do I get for my resultant matrix, which is 2 by 2 here? I end up getting this. 8 plus 0 plus 2 is actually 10. 0 plus 0 plus 3 is 3. -2 plus -7 is -9 plus 6 is -3. And 0 plus 35 is 35, and 35 plus 9 is what? 44? So I get the matrix 10, 3, -3, 44, 2 by 2. Does that make sense? Look at the next guy. I got the matrix 4, 7, 3, -1, 2, 0, 5, 6, 1, 3, -4, 5, times 6, -8, 5, 3, -2. What size is this first matrix? 3 by 4. What size is the second matrix or vector? 5 by 1. Multiply row by column. What's your problem? The number of columns on the first matrix doesn't match the number of rows in the second matrix. They got to match. They do not, so the answer is cannot do. It's a trick question. You can't multiply these guys if they're not the right dimension. But it's the columns on the first matrix and the rows on the second matrix have to actually match up and be the same number, be able to multiply these guys. So, properties of matrices. Let me pull this aside. Here we go. Properties of matrix multiplication. A is a M by N, row by columns matrix, M by N. Vectors U and V are vectors in Rn. C is a scalar. Scalar means it's a constant in the reals, element of the reals. Okay? Then, two things in terms of matrix multiplication. When you take matrix A and multiply it times two vectors that are being added, now they got to be the same size vector here, both in Rn, so this means they're n by 1s. A is m by n, so it matches up. So matrix A times vector u plus v is going to be the same thing as matrix A times vector u plus matrix A times vector v. Mathematically, please tell me what operation you would consider this to be. A being multiplied by u plus v is the same thing as AU plus AV. Distributive property. You can distribute matrices across multiple vectors, being added or subtracted. Does that make sense? The second thing is this. Matrix A times scalar C, constant C, times vector u is the same thing as scalar C times matrix A times vector u. If I describe this in English, what's going on? C is a constant, a scalar, constant. When I multiply a matrix times a constant times a vector, I can take that constant, employ him out front, and just multiply the matrix times the vector, and then multiply the constant. We multiply a constant, and you get each one of the terms. So, in other words, constants, when you're multiplying, can go out front and hold over. You can focus on your actual matrix vector multiplication, and then just multiply the constant at the end. That may save you a lot of time and effort. The other big deal here is this. Matrix A times vector x. Matrix A was m by n. Vector x was m by 1. The only way you can actually multiply matrix A times a vector x is the number of columns on matrix A has to match up to the number of rows on your vector. And then they're going to match up and cancel, and you end up getting a resultant of an m by 1 vector. Okay? So turn page. Now, we're going to be solving these systems of equation type thing here. So here we go. Another, again, introductory course, so don't panic and freak out so much about terminology. We got a lot of terminology, but the interesting thing is, how many of you guys have taken DiffyQ? You taking it now, or have you already taken it? Oh, good. We're going to pick on you guys. And what about you? You've already taken it? All right. So, in differential equations, we talk about this concept of homogeneous equations. And it sounds very impressive, but it really means it's a very simple concept. Okay? So, the solution sets of linear systems. And it's the same concept as we use in differential equations. Usually you take this class before DiffyQ, but neither one. Calc 2 is a prerequisite though. You know, for differential equations. I think Calc 1's a prerequisite for this guy. So you don't have to take algebra before differential equations. Most people do, but you don't have to. All right. First definition is this: homogeneous linear equation. That word homogeneous. A homogeneous linear system is an equation set to 0. That's all it means. You set the equation equal to 0. You know, when we have ax equals b, you got that equal to the b vector. Well, instead of the b vector, just set it equal to the 0 vector. So a homogeneous linear system is an equation set to 0. Ax equals the 0 vector. Now we're talking about vectors here. What is the 0 vector? Well, let's say the 0 vector, the vector's got to be n by 1. That's 0, 0, 0, 0, n of them. Does that make sense? It's not just set equal to 0, but it's set equal to the 0 vector. But when you talk about homogeneous in other classes, you're typically going to be setting something equal to 0. All right. With homogeneous linear systems, the vector x is the 0 vector. It is always a solution called the trivial solution. What is matrix A times a column of zeros? 0. 0 times first term, 0 times, you just get a bunch of zeros. So if you're trying to solve ax equals 0, you'll always get 0. So 0 will always be a solution. Question? Yeah.
What does that say to the homogeneous linear system on the left
This one right here,
or the left?
more or less. With this one,
Or the equation?
def. He's making fun of my notation. We're math people. Abbreviate. D-E-F-N. Definition. I could write out the word definition, but it will cost you more for me to be your professor then. All right. Definition. All right. D-E-F. You guys are really learning about professors teaching math classes. I'm telling you. How many of you guys are actually double majoring in mathematics? Good. Pick on you. Every one of your professors is going to abbreviate everything. Your engineering professor, how many guys are engineers in here? Okay? What does your engineering professors do when they write on the board? Abbreviate everything, right? Okay? Computer science guys? Well, let's see here. My professor, when I was doing the computer science stuff, he didn't write hardly anything on the board. He just told us everything and then had slideshows. So, whatever. You're on your own on that one. All right, so here we go. I'm trying to write this stuff for you guys. Here we go. So, with a homogeneous linear system vector, the vector x equals 0 is always a solution. That's called the trivial solution. When you're trying to set equals 0, 0 always works. 5 times 0 is always 0. So that's the solution for you. So a homogeneous linear system has at least one solution. You're guaranteed. So you don't have to worry about an inconsistent system, right? 0 will always work. And 5 times 0 plus 3 times 0, yeah, pretty much you get 0 out of that. So the non-trivial solution is when the vector x is not equal to 0. So we're going to look at the 0 solution and the non-trivial solution of this homogeneous. So the system ax equals 0 has a non-trivial solution if and only if the equation has at least one variable. Okay? So watch what I'm talking about here. Let's take a look at this guy here. So I gave you a system of equations. Always trying to teach through examples with this stuff. So I've got here 2x1 plus 4x2 plus 3x3 equals 0, negative x1 plus 5x2 plus 3x3 equals 0, and negative 7x1 plus 7x2 plus 3x3 equals 0. I've got this coefficient of my variables, and they're all set equal to what? 0. That's that homogeneous talking about. Now, if you go from here, you're going to write it as an augmented matrix, right? Well, first off, I'm going to write it as a matrix equation. Then I'm going to write the augmented thing here. Matrix equation. So what is this? 2, 4, 3, coefficient matrix. Negative 1, 5, 3, negative 7, 7, 3, multiplied by the vector x1, x2, x3. That's where your vectors come from. And it's equal to the vector 0, 0, 0. So you get this ax equals 0 homogeneous system. Written it as a matrix equation. This is a system of equations. This is a matrix equation. And then from the matrix equation or the system of equations, when we want to solve this stuff, what do we do with it? We write it as an augmented matrix. Very proud head for you guys. What is the augmented matrix? Basically, you take your matrix, drop the x1, x2, x3, and just move what it's equal to over there to the other side, and then you slap them together as a bigger matrix, augmented matrix. So it's actually two matrices put together. Does that make sense? Now, this is my augmented matrix. I want you to solve this guy. And if you notice, I keep practicing your skills on this stuff because I can talk a lot of theory with this stuff, and I can explain a bunch of stuff and how it's used, and that's awesome. But at the end of the day, you got to work these problems. And the problems I'm going to give you are going to be problems that actually typically have numbers in them and stuff. And where most people will mess it up is they don't know how to manipulate their numbers. I want you to solve this thing. So, if I'm going to solve this thing, I'm going to go for the reduced echelon form. What's my first move? What would you do? Where are you going to, okay, I want to pivot right there. I got a 2. Row swap with which one? Row 2. I know it's -1, but I can make a -1 into a 1 real simple, right? So I would row swap, because I really don't want to divide by 2, right? That'd give me crappy fractions, especially with the 3/2 thing here. So I'm going to do a row swap. So row 1 with row 2 swap. That's going to give me -1, 5, 3, because I'm trying not to skip steps, 0, 2, 4, 3, 0, -7, 7, 3, 0. And then, what would I do? I would do a negative row 1 and replace row 1 with it. I'm going to make them a true pivot. 1, -5, -3, -0, that's still 0. 2, 4, 3, 0, and then -7, 7, 3, 0. What's my next move? Sweep down. Take your pivot, sweep down. That one's a 2, so I'll multiply by -2 times row 1, add it to row 2, replace row 2. And then I'm going to sweep down. I got a -7, so I'm going to do 7 times row 1, add it to row 3, replace row 3. That'll leave me with 1, -5, -3, augment 0. And here we go. -2 times 1 is -2 plus 2 is 0. -2 times -5 is 10 plus 4 is what? 14. -2 times -3 is 6 plus 3 is 9. Watch this. -2 times 0 plus 0, that's still going to be 0. Now, come down here and sweep down and kill off that 7. 7 times, -7. 7 times 1 is 7 plus -7 is 0. 7 times -5 is -35. And -35 plus 7 is what? -28. And then 7 times -3 is -21 plus 3 is -18. And of course, 7 times 0 is 7 plus 0 is still, got it again. 7 times 0 is 7 times 0 is 0 plus 0 is still 0. Yeah, you get zeros over there. Does that make sense? What's your next move? You could make him a pivot, a 1 pivot, or you could just use what he is right now and sweep down. I'd sweep down because 14 and 28, that's kind of nice numbers, right? So I can sweep down. So my next move is to do what? What do I got to multiply 14 by to kill off that 28? 2. 2 times row 2 added to row 3, replace the row 3 with it. This gives me 1, -5, -3, augment 0, 0, 14, 9, 0, 0. 2 times 14 is 28 plus -28 is 0. 2 times 9 is 18 plus -18 is 0. 2 times 0 is 0 plus 0 is 0. Notice, I got a row of zeros now. What'd you do now? Well, I'm going to make him a pivot. I'm going to do 1/14. I'm sorry, but at some point, it's going to happen to you. Make him a pivot. So divide by 14. So I get 1, -5, -3, augment 0, 0, 1, 9/14. What is 0 divided by 14? That's 0. And 0, 0, 0, 0. And then I only got one more move to make. You notice I try to make my fractions until the end, but I'm sorry, you are going to deal with fractions at some point. You just try to push them off to the end and be careful on that. So now I'm going to sweep up, and I'm going to do 5 times row 2, add it to row 1, replace row 1. So I get 0, 0, 0, augment 0, 0, 1, 9 14th 0, and here we go. 0 times 5 is 0 plus 1 is 1. 5 times 1 is 5 plus negative 5 is 0. Here we go. 5 times 9 14ths is going to be what? 45 14ths plus negative 3 is going to give me a 3 14ths. 5 times 0 is 0 plus 0 is 0. So this is what I get for my resultant. Okay? 1, 0, 3 14ths, 0, 0, 1, 9 14ths, 0, 0, 0, 0, 0. Okay? So what is this telling me right here? I do not have an inconsistent system. I don't have 0 is equal to a number. This is consistent, so solve. Remember, we're trying to solve for x1, x2, x3, x1, x2, x3. You with me? I want to write it as a parametric equation, and then I'm going to talk about a parametric vector equation. You'll see how I connect the two together. So, right back to my equations. This is x1 plus 3 14ths x3 is equal to 0. The second equation is x2 plus 9 14ths x3, that's equal to 0. I only got 2 equations on this thing, right? So now, solve for the pivots. What does that make x1 equal to? Negative 3 14ths x3. I just moved it 3 14ths x3 to the other side. What is solve for the pivots? x2 is the other pivot. That's equal to moving the 9 14ths to the other side. 9 14ths x3 gives you a negative 9 14ths x3. And then, if you've got to have your variables, you've got to tell me what x3 is. But x3 was not a pivot. So if he's not a pivot, what do we call him? Free variable. And a free variable is always equal to himself. So right here, you see this guy? This is a parametric equation solution. But I want you to write this in parametric vector form, which means I want to write it as vectors. The vector is x1, x2, x3. How do I write this as a vector? You see the x3s, they're all in common. It's a constant. You can factor it out, and you just write the coefficients in the component spot. This is a negative 3 14ths. This one is a negative 9 14ths. This is x3. What's the coefficient in front of it? 1. It's 1 because that's the free variable. And this is the parametric vector form of the solution. But as you said, x3 is your free variable. It is free. Okay? Well, no. You put him as a 1 because it's 1x3. Now, you make x3 any number you want to, and then when you multiply a scalar times a vector, it's going to distribute to all these guys and scale it accordingly. Okay? So, with that, look at this one right here. Okay, so, turn my page over. Terminology is this. A parametric vector form, just get it in definition, is a form where x is equal to a vector u times a scalar x1 plus another vector u2 times a scalar x2 plus dot dot plus a vector un minus 1 times a vector xn minus 1. But maybe you can have one other little vector out here, I'll talk about him in a second, that's not connected to an x. So, as an example here is a parametric vector form, x vector, which is x1, x2, x3 is equal to 3, negative 1, 0, x1, plus 004x2. Okay? So now, this is what we're talking about in terms of parametric vector forms. And that's traditionally, with linear algebra, how we like to write our answers. So you're going to see me transitioning from, having just system of equations and writing it in parametric form to parametric vector form. We're going to be beating that the rest of the semester and stuff. Okay? The other concept is this. We talked about a homogeneous equation. What's a homogeneous equation? That's an equation where you're set equal to the constant 0, right? What is a non-homogeneous linear system? Well, we're math people, so don't think too deep. You're going to set ax equals b. You have an equation where b is not 0. You set it equals 0, it's homogeneous. You set it to equal to a vector that's not equal to 0. That is what we call non-homogeneous. Does that make sense? So an example would be something like this. Okay? x1 plus 3x2 minus 5x3 equals 4. x1 plus 4x2 minus 8x3 equals 7. And minus x3 minus 7, minus 3x1 minus 7x2 plus 9x3 equals 6. How would you write this as a matrix equation? As a matrix equation, this would be 1, 3, negative 5, 1, 4, negative 8, negative 3, negative 7, 9, multiplied, so this is your matrix A called the coefficient matrix. The X as a matrix or vector would be, what vector we have? We had an x1, x2, x3. Remember, it's row by column, so the x vector will be the column vector, x1, x2, x3. And it's going to be equal to what we call the b vector, which is what it's equal to, which is the vector in this example, 4, 7, negative 6. Does that make sense? This is a non-homogeneous. And how did you guys solve a non-homogeneous? You solved a non-homogeneous by doing what? Again, augmented matrix. By doing this. 1, 3, negative 5, augment with the 4. 1, 4, negative 8, augment with the 7. And negative 3, negative 7, 9, augment with the negative 6. And then you go and reduce echelon form this guy. And there's 3 possible answers. We've done this how many times before? You can either have consistent unique, consistent infinite, or inconsistent on this thing, if you can, which means you can't solve it at all. So with that being said, again, I just trying terminology on this one. A non-homogeneous linear system is a linear system that you're setting equal to a vector, a constant. It's not 0. Homogeneous means it's set equal to 0. Last thing here, in terms of this, is this. Can you do me this problem? Describe all of the solutions of the linear system. 2x1 minus 3x2 minus 5x3 equals 0. And I want you to put the answer in parametric vector form. Dr. Taylor, I think you left a bunch of stuff off. No, I didn't. Nowhere did we say we had to have 3 equations or 4 equations or 27 equations or whatever. I just gave you 1 equation. You can write them as a matrix if you want to, sure. 2, negative 3, negative 5. You can augment him with the old x1, x2, x3. And what's he going to be equal to? The 1 by 1 0 matrix. I don't know if that helped you out any or not, but you can write them like this if you want to. Here's the thing. Augmented matrix, fine. 2, negative 3, negative 5, augment with 0. What's your first move? I know you're looking at me like I'm crazy. Nope, you got to put him in RREF. This thing is an REF. I want him in RREF. You got to make him a pivot. I know there's no other rows, so there's no zeros, but you got to make him a pivot if you're going to put him into RREF. So this would be 1, negative 3 halves, negative 5 halves. Here we go. 0 divided by 2, it's still 0. Okay? So, that's it. I don't need to sweep down, I don't need to sweep up, because I only had one equation. But then rewriting back as an equation, this would be x1 minus 3 halves x2 minus 5 halves x3 equals 0. We want it in parametric vectored form, right? Which means solve for the pivot. What's your pivot? x1. So what's x1 going to be equal to? Move it to the other side. 3 halves x2 plus 5 halves x3. Does that make sense? But our parametric vectored form, we want it write it as x1, x2, x3, right? So you got to have an x2 and an x3. Who are x2 and x3? x1 is the pivot. x2 and x3 are not pivots. What are not pivots called in linear algebra? Free variables. These guys are free. They can be anything they want to be. So x2 would be equal to x2. x3, I am trying to line this up, is going to be equal to x3. They're free variables, right? I'm doing the same thing. I just didn't have to do a bunch of row reduction because I only had one equation. So as a parametric matrix, so you have parametric vectored form, parametric vectored form, you get this. x1, x2, x3 is equal to x2. What do you got? Pull off the coefficients. 3 halves, 1. There's no x2 down here, 0. Times x2 plus, pull off the x3s. What are they? 5/3 off the first one. There is no x3 on the second equation, 0 and 1. And now you have written the solution in a parametric vectored form. You went from one equation, and that's all you had, that one equation, and you've been able to write them in terms of a parametric vectored form. You solve for the pivot, and then you got the free variables on the other side. Infinite number of solutions is what you get on this thing. Does that make sense? Now, next time, we're going to talk about the relationship between homogeneous and non-homogeneous, which is any kind of non-homogeneous solution has a homogeneous solution and a particular solution, which goes back to your differential equation stuff. But we'll do that next time. Don't forget, study hard on your homework. We're already in the middle of section 1.5. After 1.5, we're going to jump into 1.6, word problems and applications. Yay. All right.
Last version you did at the end, x1, x2, and x3 equals.
Oh.
Can you throw up the very last thing that you just did?
Sure. Hold on. All right. Oh, got here. This one right here. So x1, I solve for my pivot. x2 equals x2 because it's a free variable. x3 equals x3, it's a free variable.
So when you're writing it in parametric vector form right here.
Yep.
So the x1,
3
why
halves.
is the 3 half?
Coefficient of the
Oh,
x2.
of
We're
course.
pulling off the x2. So there's my x2s, 3 halves and 1. Nothing down here, 0. We pulled off the x2. This is why I kind of line them up on each other. So this is 3 halves.
So 3 half and 1, 3 half and 1, 0.
This is a half. 3 halves, and this is 5 halves, 0 and 1. And this is the x3. We're pulling off the x3. There's your parametric factor.
I just was confused. Now I see.
No worries.